Hi, my name is Jonathan Wagner, and I did Spearman's rank correlation coefficient. So to start off, Spearman's rank correlation coefficient is mostly known as being an alternative to Pearson's correlation coefficient, which we learned this semester. Just a brief reminder, Pearson's relationship we are testing must look like a line, or our data must be continuous. So something like a linear line. We often violate either one or both of these assumptions, which is the reason we use Spearman's. We apply Spearman's when we are collecting data that is considered ordinal but not continuous. And ordinal data is when the distance between the categories is unknown. What does it do? It ranks the data before consumption or computation, my bad. So in this image here, we see that for the height of the flower, although like the data doesn't come in least to greatest or greatest to least, it ranks it from greatest to least. So we got 256 with a rank of 1, 234 with a rank of 2, and so on. And it also does it for our second variable within the data set, which is the width of the step. Like 32 is the highest number, so we gave that a rank of 1. It also is designed to detect monotonic relationships, which is basically saying that it's when one variable is increasing and the other is also increasing, or one variable is increasing and the other one is decreasing. So something you might run into when doing this, ranking your values, is that two values might equal one another. So if we look over here for the price of the 50-cent bottle, we see that we have 1.20 twice. But in order to figure out what rank they get, you want to see what spots they would have filled. So for example, 2 is our greatest number, so that gets rank of 1. Then we see up here, 1.80 has a rank of 2. But we don't see a rank 3. And then since there is two values here, 1.2 twice, that would be rank 3 and 4. So what you want to do in this situation is add 3 and 4, because those are the spots that would have been filling for the ranks, and you would get 7. And since there is 1.2 twice, two values, you would divide the 7 by 2, which leads to the 3.5. And then if you continue on, that would be 3 and 4. You need to remind yourself that there's no 5, and then we see 3 6s, and then there's no 7. So we see that 1 is repeated here 3 times. So that should be taking the spot of rank 5, 6, and 7. So if you add 5, 6, and 7 up, you get 18. And since there's 3 values here that all equal one another, you want to divide by 3. So 18 divided by 3 is 6. Giving those 3 values a rank of 6. After you take the ranks, you want to pretty much completely fill out this chart over here. And the next thing you'd want to find is D, which is the difference between the ranks. So that requires going back to the first variable that we had, and you just go straight across. So for the first one, we had the rank is 10, and then we saw over here for price of the bottle, it was rank of 2. So the difference between those two is 8. And you just keep going down the path and getting all your numbers. It's okay if you get a negative number. Sorry about that, because our last step is squaring it, and that'll turn it into a positive. So once you square it, then the last column is D squared. So you just square D, and that gives you this value here. We will be referring back to that picture shortly. So the reason we are computing these values is so that we can plug them into the equation. And I only recommend like the equation if you have a short data set, because if you have like 500 different things in there, it's gonna be too much work to go yourself and count them and rank them and everything like that. So this is our equation here, where the P just pretty much represents the Spearman's correlation coefficient. It also, in some equations, like you'll see, it abbreviates it as R sub S. So then it's 1 minus 6, and then you got the rest here. You got the sigma di squared, and that represents, and going back to this picture, as you can see in the bottom right-hand corner over here, that represents all the d squareds added up to one another. So you go down the column, add them up, and in this picture, we got 285.5. And then we see back in the equation that there's n squared. N is the number of pieces in the data. So once again, referring back, we had 1, 2, 3, as you can see, we had 10 pieces of data. So that would be n in this equation. And then the last part about the equation is when you plug in all the values and you arrive at your answer, you get an answer between -1 and 1. And this picture up in the top right is showing us how strong our data is. So from 0 to 1.9, it's very weak. From 0.2 to 0.39, it's considered weak. 0.4 to 0.59, it's moderate. 0.6 to 0.79, it's strong. And then 0.8 to 1, it's very strong. That's just very strong evidence showing that like whatever our study is like related to one another. So to give you a better example, I did a real world problem. For my example, I used the data that was already built into RStudio. So my data frame was MT cars, which we've worked with this semester. But I decided to only use variables miles per gallon and horsepower. So for the first part of the code, I wanted to apply the rank command that would give me the rank of the values. Pretty much what I explained in the chart, but RStudio does it for you automatically. So what I did was up in the top right here in this picture, I just did rank, and then I put in my data set and then what I was looking for, so miles per gallon. But I also assigned it to my own, I guess, homemade variable called R1, just so it'd be easier later on when I'm designing my own different variable to actually compute the correlation coefficient. So that's pretty much how you get the rank there, just putting rank and then your data set and then what you were looking for specifically within the data set. So next, I wrote a homemade function called mySpearman that takes a data frame with two variables to compare and return the Spearman's rank correlation coefficient. And that is this image here. So breaking down the code, we start off with mySpearman because that's what I was naming my data set. And it's a core.test because it's a correlation test. And then R1 and R2 because that was the name of my variables from earlier, getting the ranks. And you should use the rank in this code. And then you have method equals Spearman because that's the test we are doing, the Spearman correlation coefficient test. And then once you print that, you get this code chunk at the bottom that it returns to you. And the big thing that we are looking at is the RHO, and the RHO is an abbreviation for the Spearman's rank correlation. As you can see up here, it says RHO as well. And we see we get an answer of a negative 0.894. And what that is telling us is that when the miles per gallon is increasing, the horsepower is decreasing. And we know this is strong evidence from our image earlier. We got 0.89, and the range is from 0.8 to 1, telling us that is strong evidence. So this is my presentation. I hope you learned about Spearman's rank correlation coefficient.